So hopefully you've enjoyed this workshop and are interested in sort of applying modeling to your problems, finding collaborators, and what we thought we'd put together for this lecture is some sort of tips for finding people who may help you on your modeling journey. The first step of that is to make sure you articulate a good question. So what is the system or question that you want to model? Why do you think it needs to be modeled specifically? Why is that the tool you want to use? What kind of model do you think it needs? And then how fast do you need an answer? If you're working on an emerging infectious disease or a very rapid policy question, that may dictate what you can get done in a given span of time. So a good example of a question is, I want to study the effect of incarceration policy on neighborhood resilience. I think that there's a lot of indirect effects and feedback loops that exist, so that's why I wanted to sort of do a modeling approach. I'd like to model some fairly sophisticated behavior and people's interactions with the environment, so I'm looking at sort of an agent-based model. That's a pretty good articulation of a question. Sort of an unhelpful one is, I want to make an agent-based model of tuberculosis. What does that mean? Why do you want to use an agent-based model? Is that because you just read about them and you think they're super cool? Is that because you genuinely want to tackle a problem that needs an agent-based modeling framework? At what scale are we talking about with tuberculosis? We could model how your immune system responds to an infection within your lungs, or we can talk about the global spread of extensively drug-resistant TB. Those are both valid questions to ask using a modeling framework, so you need to sort of tune your question a little better. Modeling is inherently sort of a team science and is multidisciplinary. It's also a tool rather than a specific discipline. As much as people will, call themselves modelers or say, oh, you should go talk to so-and-so, they're a modeler. That's sort of like calling someone a hammerer. It's a tool people use. It's often a tool people use a lot, but it's not a discipline, which means there's a lot of places where modeling is used, including for epidemiologic research, that are outside traditional departments of epidemiology. If you think about the affiliations of the presenters in this workshop, none of us are in departments of epidemiology in sort of a conventional school of public health. So there's some very common places to look. Ecology is a big one. A lot of modeling is rooted in ecology, and they often use very similar methods. Vector-borne disease research is very well represented, and if you want people who are very good at sort of understanding the behaviors and distributions of vectors, the ecology department's often a very good place to start. This also lets you work in veterinary and wildlife disease problems, which I find actually really fun and really interesting. If you ever want to feel better about the amount of data you have for your question, go talk to a wildlife disease ecologist. And this applies to broader topic areas where ecology could live into. So things like biology or entomology or zoology are all places that you could potentially look. Mathematics. If you haven't picked this up by now, there's a lot of math involved in modeling. And if you're interested in analytical results, so things like proofs about how your systems behave, R-naught estimation using very complicated models, mathematics collaborators are often invaluable because this is where their expertise lies. But you can dig deeper. So economics. A lot of modeling is about understanding how people and organizations make decisions. So you can get things like cost functions or behavioral choices or cost benefits from economics, but you can also get genuine collaborators who are interested in modeling problems. So for example, some of my favorite collaborators at WSU are some economists who are interested in things like how livestock trade affects disease risk and how we determine, how goats move from one herd to another through commercial transactions and what that does for disease risk. This also means other behavioral science departments. So sociology and anthropology think a lot about how people interact with each other. I've spent a lot of time talking about approximate Bayesian computation with some computational archaeologists. These are interesting and very potentially valuable collaborations that are places that most epidemiologists wouldn't necessarily think to look. And indeed, when I was a graduate student or postdoc, I wouldn't have necessarily thought to look. So there's also other methodologists. So physicists. A lot of the methods used in modeling also get used in physics. Most compartmental models are essentially the same way you'd model molecules in a well-mixed container. So the physics department is often a very productive place to look. There can be some challenges to that, but for example, my postdoc advisor, who is a very good and very sort of committed epidemiologist, is a physicist by training. Operations research, which is the field that tries to understand how systems work, how to detect changes in those systems, and if alterations you made to a system matters, usually in terms of sort of industrial processes. But if this sort of sounds familiar to you, it should. They're also interested in optimizing systems around resource constraints. This is often very important for modeling problems. If we have a fixed number of vaccines, who do we give them to? How do we minimize everyone's travel time by where we put particular sort of vaccine clinics or something like that? These are operations research questions. Computer science. Computer science works a lot on how to make algorithms faster, the science surrounding networks, things like that. For network and agent-based models, this is often important, and this is often a very, very strong collaboration to make sure your models work reliably, they run in a reasonable time frame, and are sort of methodologically valid. So some terms to potentially look for that are sort of hints that modelers are nearby. Dynamical systems. The ODE-based compartmental models fall under dynamical systems. Complex systems is essentially the study of how patterns emerge from interactions between things. So most of modeling falls under complex systems. Stochastic systems is like dynamical systems, but for stochastic models. System science is the broader sort of idea of studying how systems work as a thing. Disease dynamics is another word for modeling. So for example, infectious disease dynamics or iddjobs.com is where a lot of modelers go to find postdocs and things like that. Graph theory and or network science if you're interested in networks. And then mathematical biology is how a lot of modelers in either math or biology describe themselves. So these are some places you can potentially go to look. Really, the answer is to sort of dig deep, take a very broad approach to things. Don't be afraid to sort of go to seminars in different departments and see what they're up to. And then reach out to those people and talk about potential collaborations. Many of my most fruitful collaborations are with colleagues in departments that I wouldn't necessarily have expected them to be in.